New stuff.
You know someone too?
No, I'm that person.
You are that person? Is that what you just said? Oh my God. I should have therapists waiting in the hall for everyone to admit it on the way out the door. Let's see, new stuff. Is this where we're at? Here's where we're at. This is it. This is the 5th equation of the 5 equations that will be on quiz 3 a week and 2 days from now. Proportions. Proportions. I want to tell you, this shouldn't be that hard, okay? You should start to see a trend how all of these equations have such common features to them. We started this whole semester with confidence intervals, but there was population standard deviations, sample standard deviations, and no standard deviation, which was proportions. And then we went to a whole section with one sample hypothesis testing, but the same situation. Population standard deviations, sample standard deviations, no standard deviations, which was proportions. And now here we are with 2 sample hypothesis testing, and we went through population standard deviations, 2 equations where there's sample standard deviations, then we went through paired matched samples, which is kind of different, and here we are where there'll be no standard deviation at all, and this is proportions. The 5th of the 5 equations that will be on quiz 3, which is 2 sample hypothesis testing. So, here's the deal with proportions. I'm gonna mention these little rules that allows this proportion technique to work, which is the same rules on proportions that we had when it was 1 sample hypothesis testing, but it's a little expansion to it. And I want to tell you on quiz 3 and on your homework, I'm not tricking you. You don't need to worry about these rules. The problems we're gonna do will meet these rules. You don't have to worry about it. But I do have to mention these because in real life, if you guys do go on to your master's and you do want to do proportions as your thesis for your master's, you do need to mention that these rules are met when you're applying the data, if you happen to do proportions. And it says, let me make sure I'm turning these variables into words. Sample size 1 times proportion number 1 has to be greater than or equal to 5. All 4 of these have to be true at the same time. I want to make sure you realize that. Not just one of these, all of them at the same time must be true. The sample size for number 2 sample, proportion number 2 when multiplied had to be greater than or equal to 5. Then you have sample size number 1 times the opposite of the proportion number 1. 1 minus the first proportion has to be greater than or equal to 5. And then sample size number 2 times 1 minus the second proportion, the opposite of the proportion, has to be greater than or equal to 5. All 4 of these will be true on any problem I give you for this class. You don't have to worry about that. You don't have to even investigate that. But in real life, those 4 all have to be true at the same time for this to work, to have meaning. All right, P1 minus P2, that's the numerator of your test statistic equation. That's the left-hand side before the plus minus of your confidence interval equation. That just says the first proportion minus the second proportion. Here is what's called the pooled proportion. Now let me point out pooled proportion. In the denominator of your test statistic is the pooled proportion times 1 minus the pooled proportion. So it's in this equation, and then your confidence interval equation has the square under the square root, pooled proportion times 1 minus the pooled proportion. The pooled proportion is not that big though. It just says add up however many out of however many. So if it said 15 out of 20 and 10 out of 20, you would have 15 plus 10, 20 plus 20. All of those out of, however many out of in your denominator, and however many successes they're called in your numerator. So it's just putting the 2 proportions together and turn it into 1 proportion called a pooled proportion. It's the average of the proportions, really, is what it is. So now, here's the equation in variables. But here's the deal. Just like that, all 5 equations for this 3rd quiz, we're ignoring the top right-hand side of the numerator because this is always 0 for this class. This will always be 0. So any proportion minus 0 is always the original here. So there's no reason to even talk about it or even do anything with it. It will always be 0. You might as well just take it right out of the equation. If you notice, I don't have it in here at all in either of these equations. It's just 0. It's nothing for this class. It's basically saying if one proportion not different from another, then they'd be darn close to zero. And that's where the zero comes in. If they are different from each other, one proportion is different from the other, they would be away from zero then, when you subtract them. There's no way there'd be a zero. So, there's the formula. The only part I haven't described to you, I'm gonna describe the whole thing. Proportion 1 minus proportion 2 is your numerator, and you must subtract those before you do any of this other division part here. Underneath the square root is this whole thing in the denominator. Pooled proportion times 1 minus the pooled proportion times, here's the weird part, 1 over the first sample size plus 1 over the sample size, second sample size. I start with these two sample sizes when I do this problem. I'll get 1 over the first one plus 1 over the second one, add them together. Then I'll take pooled proportion times 1 minus the pooled proportion, then I'll multiply these two, then I square root it, then I divide it into this difference. That's pretty much the order I go in. I attack the denominator and divide it in the numerator at the end there.
Do we call that the margin of error underneath it, or?
This is the margin of error, yes.
Okay.
No.
No.
I'm sorry. Here's the margin of error. This is the standard error.
Standard error.
Standard error is from this point over, when you add the critical value, then it's the margin of error. This is the standard error, is the denominator.
Okay, standard
Which
error.
is this right-hand side, the same denominator as the right-hand side of the confidence interval. The only part you're adding here is you're multiplying it times the critical value. Add and subtracted them to the two proportions. So you have your critical value approach. It's what you don't see here, is just using, once you have this test statistic, you compare it to that critical value. You're gonna get the test statistic for the p-value approach. Here's the confidence interval approach. I forgot to bring up those 5 equations, the same equations we've used almost the whole semester now. Let me go back to from week 5 is when I made this. Let me bring it back up. Let's get the 5 equations up here. Here they are, here they are, here are the 5, and here's the little rules. Now, here's everything. Are we ready to attack one of the problems? We're gonna do all 3 approaches when we attack this problem.
For the pool proportion, I understand that the denominator is the sample, but what is the numerator?
The numerator is like how many out of the sample size. So let's say, well, let me show you this problem. This one says that 36 out of 72 men, the 36 is the X, and the 72 is the N. And then the other one is 31 out of 50. So you would take 36 plus 31 for your numerator, the two X's. 36 plus 31. And then out of how many? 72 and 50, your two sample sizes. 72 plus 50. There is your pooled proportion. By the way, the right-hand side of your alternative hypothesis is the exact same 3 choices you have in this whole semester. Less than, greater than, or not equal to. That's the alternative. The null hypothesis, greater than equal, less than equal, or equal to. These have been the exact same 3 choices for an alternative and the 3 choices for a null the whole semester. So nothing's changed in there. Notice I want to remind you, because there's still a couple people who are missing this, the equal sign can only be in the null hypothesis. Whether it's greater than equal, less than equal, or just plain equal, it must be in the null. It cannot be in the alternative. And notice for these two sample hypothesis testing, the right-hand side is always 0. All right, here's our first example. We're going to do all 3 approaches. Is there a significant difference between the proportion of men and the proportion of women who will vote yes on proposal A? One tail or two tail? Why?
Because it says difference between, so I'm gonna.
Difference, that's the key word. It's asking if there's a difference between these 2 proportions. Is there a difference? It didn't say, do the proportion of men exceed the proportion of women that are gonna vote for proposal A? It doesn't say, does the proportion of women exceed the proportion of men? It says, is there a difference? That's how we know it's two-tailed. Okay, so that's gonna be right here, the far right-hand side. One proportion minus the other proportion equals 0 is your null. One proportion minus the other proportion not equal to 0 is your alternative, right there. What significance we're using? 5%. Says, in a random sample of 72 men, 36 said they're gonna vote for proposal A. A random sample of 50 women, 31 said they're gonna vote for proposal A. There's our two proportions. 36 divided by 72, 31 divided by 50. We gotta turn those into decimals and plug them into our formula. So here we go. 36 divided by 70 is 0.50, 50% men. 31 divided by 50 is 0.62, 62% women. Think about the numerator of your test statistic. The numerator of your test statistic is going to be positive or negative. We're looking at those two proportions. 0.50 and 0.62 is the numerator of your test statistic, positive or negative. I can't hear you. I hear negative because it'd be 0.50 minus 0.62. It would be a negative 0.12. So if this were a one-tail, and it's not, but if this were a one-tail, the alternative hypothesis would be either less than or greater than which one? Less than, very good. Very good. You're getting it. Oh, we're gonna ace this third quiz, I feel it. Our average is gonna be over 80. I'm gonna have to curve it down. What? What? Oh, that's not allowed.
Is that a possibility?
It is. Anything's possible. So now we gotta find our pooled proportion. We add up the numerators, we add up the denominators. It was 36 out of 72, so here's the 36 out of 72. 31 out of 50, so here's the 31 out of 50. We add the 36 and 31, we add the 72 and 50. This is the same as finding the weighted average of the proportions. So notice it's not right in the middle between 50 and 62 because we had different size samples. So we end up at 0.549. Basically 55%. That's our pool proportion. And I want you to think of this equation right here, the denominator. This is, what was it, 0.55? I'm rounding, 0.549. 0.549 times 1 minus 0.549 times 1 over the sample size for the first one is 72, plus 1 over the sample size for the second one, which is 50. There's the setup for this test statistic, where if this is p-value approach, that'd be most of the points right there. Or critical value approach, that'd be most of the points right there, is that setup. The numerator is 0.50 minus 0.62. Here's what we get. 0.50 minus 0.62 minus 0, but we're ignoring that 0 in the numerator. 0.549 times 1 minus 0.549 times 1 over 72, 1 over 50. Square root the whole denominator. You're going to show me two calculations, right? If you're taking the quiz, just at least two calculations involved. Negative 1.31. Wait a minute. Critical value, plus and minus 1.96. Wait a minute. We got to stop here. How did we find that critical value? Here we go. Equals norm or T? Normal T on this proportion.
It's gonna be
Why norm? Z. Proportions are always Z. Norm INV or norm DIST?
inverse.
INV? Okay, hang on, let's look at the rules. I want to make sure I do it right. Here we go, we're saying this fourth one down right here. Norm SINV, I forgot the S. Norm SINV, parentheses. The first number is going to be the confidence, and it says if it's a two-tail, use the confidence plus half significance. All right, and is this one a two-tail?
Yes.
So let's go back to the problem. Let's go back to the confidence. What's the confidence of this problem? 95. It didn't even give you the confidence. I'm proud of you, proud of you, proud of you, proud of you, proud of you. Everyone said 95 because it says 5% significance. So you know the opposite of the confidence. And it says to put in there the confidence plus half the significance. So we're not putting 0.95 because this is a two-tail. We're putting point what? 0.9 what? 75. Parentheses. That's how you get the 1.96. Somebody check this to make sure. Hang on, let me go back to the math. But it should be plus or minus 1.96. There is our critical value, right there. Our our Z test statistic is negative 1.31. There's negative 1.96 to the far left. There's positive 1.96 to the far right. Negative 1.31 lands between the two critical values, which means we cannot reject. We do not have significant evidence that there is a difference between the proportions of men and women, which surprises me. Look at how wide the gap is, 50% versus 62. Yet, that was not wide enough of a gap of proportions of who's gonna vote for proposal A to be able to state that was a significant difference at 5%. I bet if we changed this to 10%, that would have been a significant difference. I don't know, was that close? Oh, maybe not, that's not that close, is it? 1.31 to 1.96 negative? It's not that close. All right, there's our critical value approach. Let's, since we have the critical value right there, help me set this up, because this is where all the work is. Help me set this up. What's this first number right here?
0.50.
0.50, what's the second number?
0.62.
0.62, what's this number right here, critical value?
1.96.
1.96 times pool proportion. Point what?
Negative 1.3.
No negative on pool proportion, that's impossible. Let me go up here and look. I see the pool proportion, what goes here? Point what?
0.549.
0.549. 1 minus what?
0.549.
0.549. 1 over?
70.
Point what?
No, 72.
No, nothing, point 72. 1 over?
50.
50. There's the setup. You got it. You do the math on it, I did the math on it, and I posted this worksheet right here. Let me make it bigger. Confidence intervals down here. I moved this up. There it is. What you told me, 0.50 minus 0.62, 1.96 square root, 0.549, 1 minus 0.549, blah, blah, blah. There's a couple of calculations. I get an interval of negative 0.2995 and positive 0.0595. One of the numbers is negative, one of the numbers is positive, so we know 0 does fit between the two confidence intervals, which means we cannot reject the null hypothesis using confidence interval. Now there's one more, p-value. Before I show you p-value answer, help me here, equals NORM dot DIST. Let's review the rules. Let's review the rules. I know it's a t-test. Whoop. So it's oh, am I supposed to use 1 minus or a positive? Was the test statistic negative or positive? I gotta go back and look. What's the test statistic? There it is. Negative 1.31. So we use the top one, which is what I wrote just by luck. Negative test statistic would be negative 1.31, comma. Then it says use your 0, 1, 1, 0, comma, 1, comma, 1. There it is. You plug that in. Don't forget the equal sign while you're taking your quiz. You plug that into Excel. Wait, was there a rule I passed here? Multiply by 2 if it's two-tailed. Oh, hang on, I gotta get, not this Excel spreadsheet, we need another one. Someone already do it? Here we go.
1.80.
Is it before you multiplied it?
No.
Oh, equals norm dot DIST negative 1.3 what? 1.31, is that correct? 0, comma, 1, comma, 1, parenthesis.
0.1.
Uh-oh, what did I do wrong? I got a negative right there somehow. What else did I do wrong? How come you're getting 08 and I'm getting 09?
No, times it by 2.
Oh, okay. Now take this, I'm gonna take cell, what is this, H10? Equals H10 times 2. 0.19, is that what you got? Everyone? 0.19? Let's look. Where is this? This is this one right here. We're going up to p-value now. Here it is, test statistic is negative 1.31 and the significance is equal to 5% if it's two-tailed. Using the Excel norm DIST, I get 0.0968, but you gotta multiply it times 2 because it's two-tailed. 0.1936, everybody saw that is what we got. Since 0.1936 p-value is greater than 5%, boy, that's much greater than 5%, the null hypothesis cannot be rejected. We just did all 3 approaches using proportions with no standard deviation. Oh my gosh, this quiz is gonna be too easy now. We could have this homework done right now. I don't even know why we're not done with the homework. There's no Excel this week in the homework. Let's look at this week. Let's see. The instructions said we have a written assignment. It says open the document named DS302 week winter 3rd 25 week 10 homework. Answer the questions due before 2 p.m. Monday, March 24th. 2 days before the quiz, which is on March 26th, which is a week from this Wednesday. The usual materials are on there. And now let me show you the homework. Here's the homework. The first problem, use the following hypothesis and sample data for the answer to the question. Proportion 1 minus proportion 2 equals 0. Proportion 1 minus proportion 2 not equals 0. And we know it's a two-tail. Significance 10%. X1 is 231. N1 is 420. This is 231 out of 420. Oh, I'm giving away the homework now, aren't I? Let me keep going. Blah, blah, blah. Second one is a story. By the way, the first one's asking you to use p-value approach. Why is it not? Let me fold that up there. Boom. P-value approach. Let me save. The second one is doing a proportion. There's the story, but it's asking you to use confidence interval approach. The third one is another different story, and it's asking you to use critical value approach. So you have 3 proportion problems, no Excel this week, and all 3 of them, each of them are asking you to use a different approach. They're different stories. Number 2 and number 3 is asking for that final sentence as to what it means. And so you've just now been given enough information to do all that homework. Lexi, you're on.
Oh, for the norm.dis, it's always 0, 1, 1.
Yeah, it is.
Right?
For the norm.dis, whether it's the 1 minus in front or this one, it's 0, 1, 1 for those 3 numbers.
Okay,
If you want to
thank
use
you.
that one, that's, if you want to use these 5 equations, whoops. Yeah, those both have 0, 1, 1. And then you get both of them, say multiply by 2 if they're two-tailed. All right, you ready to see another example? Ready to go over it? You're gonna talk me through it? We're gonna set it up, all 3 approaches. Here it is. Let me get ready because the enthusiasm is overwhelming.
Yeah.
Feel it too, huh? Research by analysts and retailers claims gender differences when it comes to online shopping. Okay, from that sentence, you would think it's one tail or two tail from that sentence alone. You would, wouldn't you? Hang on, though. Sometimes you gotta read the whole problem before you make a decision. But at first, I thought the same thing. It sounds like it's a two-tail. A survey received that 5,400 out of 6,000 men said they regularly or occasionally make purchases online, compared with 8,600 out of 10,000 women surveyed saying the same thing. At 5% significance level, test whether the proportion of men who regularly or occasionally make purchases online is greater than the proportion of women. Now, one tail or two tail? One tail, because they switched it up at the end there and said greater than. That was kind of shocking. Not many problems do that. I wouldn't try to trick you like that on the quiz, not on purpose at least. I would probably have use the word greater up in the initial sentence up top, so you know it's one tail to start with. All right, now, don't forget, when we calculate a test statistic here, wait, is this one tail? Yeah, it's one tail. Don't tell me what the alternative is. Kind of think to yourself, try to imagine before. All we gotta do is look at the numerator of the test statistics. All right, once we look at the numerator of the test statistic, we'll know if the alternative is a less than or greater than. But I want you to picture in your mind, since we're testing that the proportion of men shopping online is greater than women, let's hypothetically make a proportion for men, make a proportion for women, subtract them and see if the number is above 0 or below 0. And that is another way to tell whether your alternative hypothesis should be greater than or less than. So make up give me a proportion for men. Make one up out of the blue. 50%. Now give me a proportion for women that's less than 50. 40. What's 50% minus 40%? 10%. Is it above 0 or below 0? Above 0. Would your alternative be greater than or less than? Greater than. There it is. You just solved it without even getting to it. But when you get to the point of doing your test statistic, whatever that numerator part turns out to be will confirm if your alternative should be greater than or less than if it's a one tail.
But what was the assumption that the proportion for women is less than the proportion for men?
We're assuming for this person to do a whole research study on if the proportion of men is greater than the proportion of women, it means that the results probably turned out to where the proportion of men is greater than women. But all we're trying to figure out is it far enough greater to be significant, or could it have been randomness that caused men to be more? So, if we took 5,400 divided by 6,000, let me put this down here right now. 5,400 divided by 6,000 is one proportion. And the other one's gonna be, what is it, 8,600 divided, this one's easy. 8,600 divided by 10,000 is easy. That equals 0.86. There's that.
0.9.
Well, this one's 0.9
Yeah.
on the nose? 0.90? Okay, 0.90.
Yeah.
So there we go. Think of your numerator now. 0.90 minus 0.86 is a positive result, so you know your alternative must be greater than. Oh my God, this class is too easy. Let's take it again. Let's take advanced statistics, just to keep going. We're on a roll.
Is there a class? Advanced class?
Yeah, we should have a third one, that's what I'm saying. By the way, 44 days, 44 days, 44 days, 44 days. All right. Here we go. There it is. Whoops, I go too far. There it is. The alternative is greater than, because our numerator is gonna be greater than 0. So there's the alternative greater than. The null is less than equal. Here's our formula right there, same formula we have right up here. That P with a line over it stands for pool proportion. Let's talk about pool proportion. Hit me up with the numbers. I'm gonna calculate my pool. Give me the numbers on the numerator.
400.
5,400
Plus 8,600.
plus 8,600
Plus
over
6,000.
6,000 plus
10,000.
10,000. There's my pool proportion right there. I mean, this is pretty easy stuff.
14.
Let me scroll down. Let's take a look at our pool proportion, see what it is. Our first proportion is 0.90. Our second proportion is 0.86. Is the sample size times the first proportion, or is this pool proportion? We're just checking pool proportion. I don't know. It doesn't matter. They all exceed 5. All of them exceed 5. They will. You don't even have to check that. Now, time for our pool proportion. 5,400 plus 8,600 on the numerator, 6,000 plus 10,000 numerator, 0.875. So this is going to be 0.875. There we go. Here's where the points are in the setup. You know what the setup's going to be. 0.90 minus 0.86 is your numerator. 0.875 times 1 minus 0.875 times 1 over 6,000 plus 1 over 10,000, and then that whole denominator square rooted. Don't forget, the whole denominator square rooted. That's the last thing you do before you divide into the numerators, that's square root. Look at Z, 7.41. What's weird about this Z? 7.41, why is that weird?
It exceeds 0?
It's so large. We always have like 1 point something, 2 point something, maybe 3 point something. I don't think we've had one that's been over 3 point something. And this one's 7.41. Do you think you're rejecting or not rejecting the null hypothesis based on that number being so large? Rejecting or not rejecting the null hypothesis? Rejecting. Think about what the critical value is. The critical value could be 3, and that's still outside the critical value. Plus or minus 3, plus or minus 2, plus or minus 1. That's outside of every critical value we would ever use based on significance. So you know we're rejecting the null hypothesis. Let's keep going. So it says the p-value, p-value, they got, what is it? The p-value is approximately 0. Now let's do that. Let's test that theory and see if it is. Do we get a number that has that e to the power, or is it just gonna be some long number? Let's take a look. So we're gonna go p-value equals norm dot dist parentheses. It was, this is a positive 7. I gotta put 1 minus in front. 1 minus, and it was a positive 7 point, what was it? 4.1, thank you. Comma 0, comma 1, comma 1. Is this one tail, so we don't have to multiply by 2. So here's our p-value. There's that e. So let's tell me how many places am I moving that decimal, and in what direction? 14 times and to the left. So if I move it once, now it's in front of the 6. So there's 1 time. I have 13 more moves to do, so that means there's 13 zeros in front of that 6. 0.00000 13 times 6,31717. That's so many zeros in front of that 6 that you might as well call it 0. That it's 0 p-value. It's so far below 5% or whatever the significance is. Let's go back and look at what the significance is of this problem. I already forgot. What is the significance of this problem? 5%. It says the p-value for 7.41 is approximately 0. Since the p-value is less than our significance of 5%, we reject the null hypothesis. Now here's our don't look at that concluding sentence. I want us to say it ourselves. Let me go back to the story. The story is all about if there's a gender difference, is there a larger proportion of men than there are women that go shopping online, buy things online? This is the whole story. We just rejected the null hypothesis. So here we go. There is evidence, we have evidence that there is a larger proportion of men shopping online than there are women, right? Isn't that what we basically proved? We proved it without a doubt. 7.41 is so far off the charts that it's saying for sure there's more men. Now I want to tell you, before I ever read this, I don't know if this is true or not, I would have guessed there would be more women shopping online, because my neighbors have the Amazon and FedEx trucks delivering every single day, and they're coming back 3 times a day. I don't know what that means, other than all my neighbors are women. I don't know. FedEx trucks and Amazon trucks are tearing up our road. They're just coming through our neighborhood so quick. Am I the only one? Don't you guys have it coming through your neighborhoods?
Yeah.
Yeah, these trucks every day. Do they give the little honk before they jump out of the truck thinking as if the neighbor's gonna come to the door?
No.
I'm the only one that has to hear that?
Only UPS does this.
Oh, UPS? Yeah, the UPS too, I got those coming through too. Alright. Alright, so what approach did we just do? Critical value? P-value, thank you. We did p-value? Alright, so I went ahead and posted critical value approach and confidence interval approach. So these documents are posted so we can talk about the critical value approach. Here's our Z, 7.4066 or 7.41. Here's our critical value, norm.s.a&v, 0.95. Why am I using 0.95? Why? What was the significance of this problem? 5%, the opposite is 0.95, but why am I not adding to the half of the significance? One tail, so you only have to use the confidence. 1.645, 7.4041 is way outside the critical value, plus and minus. By the way, this should be plus and minus. I'm changing this as if it matters. Boom. Plus and minus 1.645, we reject the null hypothesis. Let's go now to the confidence interval. Here's the setup. 0.90 minus 0.86 plus and minus 1.645 times the square root. Let me get the graphics out of there. The pooled variant, the pooled proportion, 0.875, 1 minus 0.875, 1 over 6,000, 1 over 10,000. Square root that whole thing. Show at least 2 calculations. There I have 3 calculations. Here's our lower, 0.031116. Here's our upper, 0.048884. They're both positive. Therefore, our hypothesized 0 cannot fit between these 2 numbers, which means we can reject the null hypothesis. Both numbers are positive, so 0 can't fit. You've now seen 2 examples using all 3 approaches with proportions. This is probably the easiest part that will be on this next quiz of this section between the second quiz and third quiz is the proportions. They're just that easy.
Are all 3 approaches always gonna give you the same?
Always gonna give you the same result. Either they're all rejecting or they're all not rejecting. Yeah, on that homework where you're using the same information but used a different approach for number 3 than you did for number 2 on the written part, if you got reject on one and not rejecting the other, you made a mistake. You should have got the same answer. There's just 2 different approaches with the same information. Any questions? Any questions? Let me look at my notes here. So, I have 2, oh, I gotta shut this off. I have 2 things we could talk about. Some of you have already heard my little lecture about how you should be handling your 401ks when you're all out there after graduation making more money.